Here's something that genuinely threw me. There's a device in your kitchen right now with no moving parts, no battery, no wires, and it can keep coffee scalding hot for 12 hours by doing almost nothing. It works by removing something rather than adding it. I'll get to it at number 1, because once you understand it, you'll never look at a flask the same way. But first, 9 other everyday machines that are far cleverer than they have any right to be. We'll start with something you used this morning. A zipper looks like 2 rows of teeth, but that's not how it grips. Look closely, and each tooth has a little hook and a hollow. As the slider passes, its Y-shaped channel forces each tooth's hook into the hollow of the one opposite, alternating left-right, left-right. It's not friction holding your jacket shut, it's mechanical interlocking, thousands of tiny latches. Gideon Sundback perfected it in 1913. The really clever bit, the slider does all the thinking, the teeth are dumb. Speaking of dumb components doing smart work, look at your pen. The ballpoint pen solved a problem that beat inventors for decades. A fountain pen leaks or pencil smudges. Laszlo Barreau's answer was a tiny ball, about 1 millimeter wide, seated in a socket so precisely it can rotate freely, but ink can't flood past. As you write, the ball rolls, picking up thick ink from the reservoir on top and laying it down on the paper below, like a microscopic paint roller. The ink is deliberately gluey so it won't dribble but goes runny under the shearing force of the ball. Every letter you write is that ball rotating in 3 dimensions at once. And it never runs dry mid-word, unlike our next machine, which is doing something to your food that sounds impossible. Here's a myth I want to kill. Microwaves do not heat from the inside out, and they don't cook by vibrating molecules at their resonant frequencies. That's wrong. What actually happens, the magnetron pumps out radio waves at 245 GHz, and water molecules are polar, meaning one end is slightly positive, the other negative. The wave's electric field flips direction 2.5 billion times a second, and the water molecules flip to follow it, twisting back and forth, barging into their neighbors. That friction is your heat. It's why dry ceramic stays cool and wet food gets hot. Simple, brutal, and invisible. Now, from invisible waves to invisible sound, noise cancelling. Noise-cancelling headphones do something that feels like magic but is pure physics. A tiny microphone on the outside listens to the drone of, say, a plane engine. A chip analyzes that sound wave and generates a mirror image of it, the exact opposite, peak for trough, and plays it into your ear a fraction of a millisecond later. When a wave meets its perfect inverse, they cancel, destructive interference, and the roar just vanishes. It works brilliantly on constant low rumbles but struggles with sudden speech because it can't predict what it hasn't heard yet. The whole thing hinges on doing the maths faster than sound travels. Our next one also races the clock, but it's counting time itself. Your quartz watch keeps time using a sliver of crystal shaped like a tiny tuning fork, thinner than a hair. Quartz is piezoelectric. Squeeze it and it makes a voltage. Apply a voltage and it flexes, so the watch runs current through it, and that fork vibrates at exactly 32,768 times per second. Why that oddly specific number? It's 2 to the power of 15, so the circuit can halve it 15 times with simple digital logic and land on precisely 1 tick per second. That's the ratchet you feel in the second hand. A cheap quartz watch is accurate to about 15 seconds a month. Beautiful engineering. But the next one has no electronics at all, just shaped metal. A pin tumbler lock is a puzzle you solve with metal. Inside the cylinder are 5 or 6 spring-loaded stacks, each split into 2 pins of different lengths. With no key in, those splits sit at random heights, jamming the plug so it can't turn. Push in the correct key, and its jagged profile lifts every stack so that every single split lines up exactly at the shear line, the gap between the plug and the housing. Now nothing crosses that line, and the housing. Now nothing crosses that line, and the plug spins. Lock picking is just doing that 1 pin at a time by feel. It's a design from ancient Egypt, refined by Linus Yale in the 1860s, still in your front door. Next, a screen that knows exactly where your finger is. Your phone screen doesn't feel pressure, it feels you steal electricity. Under the glass is a grid of transparent electrodes holding a tiny electrical charge, an electrostatic field. Your body is slightly conductive, so when your fingertip gets close, it draws off a minuscule amount of that charge. We're talking picofarads. The controller measures exactly where the field dipped, on the X grid and the Y grid, and that's your touch point. That's why it ignores a gloved finger or a pencil. No conductivity, no theft. And it's why the screen sometimes goes mad in the rain. Water conducts too, and confuses the grid. Now, from stealing charge to storing it, the humble battery is stranger than you think. A battery is a controlled chemical fight. Inside are two materials that both want electrons, but one wants them far more. Connect them through a circuit and electrons stream from the eager giver through your device doing work to the greedy taker, while ions shuffle through the electrolyte inside to keep the charge balanced. The clever part is that the reaction physically cannot happen through the battery itself. The electrons are forced to take the long way round, through your phone. That detour is the entire point. When the reactive materials are used up, it's flat. Rechargeables just run the whole reaction backwards. 2 more to go, and this next one is a machine that cools by pretending to be a heater. Your fridge doesn't make cold. Cold isn't a thing you can make. It moves heat, and it does it by abusing a simple rule. When you compress a gas, it heats up, and when you let it expand, it goes cold. A refrigerant is pumped around a loop.